VSEPR Theory. Where does it come from? Do you remember what we learned about charges in physics? Well, a positive and negative particle will attract, whereas two positive particles or two negative particles will repel. This principle applies to all molecules, making them to form shapes that help us to predict the types of reactions and chemical properties. VSEPR comes from valence, shell, electron, path, repulsion, and is a theory that helps us explain and predict these geometric shapes. Let's analyze its meaning. Valence shell. If you remember, we learned about valence electrons and valence shell when working with electron configuration. And it means the electrons located in the last energy level orbit shell, which is the one responsible of chemical reactions. Electron path. Also, when covering box diagram in electron configuration, we'll learn from Pauli's exclusion principle that in each shell or box, only two electrons can be placed, and they must have opposite spins, clockwise and counterclockwise. Repulsion. The force of repulsion among the electrons is the electrostatic force, which is considered one of the strongest forces in chemical bonding and responsible of geometric shapes these molecules acquire. Let's sum up. VSEPR theory will help us predict the shape a molecule will have caused by the interaction of its electrons in the valence shell, affecting its physical and chemical properties. Facts to consider when working with VSEPR. Atoms in a molecule are bound together by electron paths. These are called bonding paths. More than one set of bonding pairs of electrons may bind any two atoms together, causing multiple bonding. Some atoms in a molecule may also possess pairs of electrons not involved in bonding. These are called lone pairs or non-bonded pairs. The bonding pairs and lone pairs around any particular atom in a molecule try to stay as far as possible from each other, as electron pairs are negatively charged and will repel each other. Lone pairs occupy more space than bonding electron pairs. Double bonds occupy more space than single bonds. Now, there are some steps that we can follow in order to do VSEPR geometry prediction. The first one is to draw the Lewis dot diagram of the molecule. In our case, we're analyzing water. And this is the Lewis dot diagram for it. Second, determine the central atom in the molecule. From a Lewis dot diagram, the central atom obviously is oxygen. Determine the number of bonding groups. In our example, as we can see, we have two bonding groups. And finally, determine the number of electron pairs that didn't bond, that are called the lone electrons. In our example, also, there are two non-bonding electron pairs. And with this, we can compare with the different structures and decide which geometric shape is this molecule taking. Let's take a look at them. Most common VSEPR shapes. And we start with the linear triatomic. In the linear triatomic, we have two bonding groups, as we can see, and no bonding electron pairs unused. Everything is used in it, and is causing a 180 degrees in the shape, making it linear. Our example, carbon dioxide. The next shape is bent, very similar to the previous one with two bonding groups, but it can have one or two pairs of electrons unused. In our example, it's only one pair, and is sulfur dioxide. We pass to 3 bonding groups with trigonal planar. In here, we can see no pairs of electrons unused. Our example is boron trifluoride, and we can see a 120 degrees separation between each one of them. The next one is very similar, also with 3 bonding groups, but we have 1 pair of electrons unused. Our example is nitrogen trihydride, and we can see the lone pair of electrons on top and pushing the hydrogen ions down, making a 107 degrees separation between them. The next one, also with 3 bonding groups, is the T-shape. In the T-shape, we have 2 pairs of electrons unused, and these push the atoms in a T structure with 90 degrees separation between them. The example in here, chlorine trifluoride. Our next example is with 4 bonding groups, no electrons left unused, and we have what is called tetrahedral. Tetrahedral makes a 109.5 degrees separation between them. In our example is carbon tetrahydride. Following with 4 bonding groups, but this time with 1 pair of electrons unused, we have the seesaw. In the seesaw is like a straight line, and we have 2 atoms in the middle that are separated by the interaction of the electrons. Our example is sulfur tetrafluoride. The next one, also with 4 bonding groups, but this time with 2 pairs of electrons unused, and this is called square planar. In a square planar, these 2 pairs make a cross shape that we call it square planar with 90 degrees separation between them in one plane. Our example, xenon tetrafluoride. Another shape, but this time with 5 bonding groups, no electrons unused, is the trigonal bipyramidal. In this shape, we can see, back again, is very similar to the seesaw, but this time we have 3 atoms in the middle axis. The example is phosphorus pentafluoride. Now, octahedral. In octahedral, we have 6 bonding groups, no pairs of electrons unused, and we have a 90 degrees separation between all of them. Our example is sulfur hexafluoride. There are more shapes, obviously, but these are the most common ones. I hope this video helped you out. Thank you for watching.